Back, everyone. It's a real pleasure to introduce Santosh Vempala, who's been here many times before. He's talked about things of relevant to this workshop in his work on neuroidal assemblies in the brain and language in the brain, I guess. But today he'll tell us about hallucinations and LLMs. So.
Sorry, I couldn't be here earlier in the week, and there are two topics here that I feel are on the edges of what we know about language models. I am a theoretician, so I'll say some things just to make sure you know how little I know or what I know about language models. But the first part is going to be basically a definition. And the second part is going to be a theorem. So one definition, one theorem, and they are not related. One will be about understanding, and one will be about hallucinations. Okay. I got some helpful feedback from Umesh last night. Thank you. And that was to say up front what is my, what I really want to say. So let's do that, and please interrupt at any point. So the first thing I want to say is that the understanding work is by Measurable Reed, who's a PhD student at Georgia Tech. And she'll present it at AAAI conference. It's coming up next. And the second part on hallucinations is work by Adam Kalai, who moved to OpenAI because he's concerned for AI safety. That's really his reason. He's still concerned. So I'll raise that at the very end. Okay. So understanding. And so yeah, you often get this, right? Oh yeah, it's answering, it seems to be correct, but does it really understand? And this we see with our students too, of course, right? They can, especially in this age when you can get your answer from the internet or from a bot. Do they really understand? But we have ways, at least for certain domains, to figure out or be convinced that they do understand. And so the point of this work is to try to define this, maybe create a measurable scale. And so I can't hope to do this broadly. This is a subject of philosophy and cognitive science, but specifically, what does it mean to understand an algorithm? Or can we measure your understanding of an algorithm? Right? Everybody who's done computer science thinks they understand Dijkstra's, great, or they understand maybe a max flow algorithm. So do they really understand? Okay, great. These are the co-authors. And so why would you want to do this? Well, can you trust the AI, understand running the algorithm? There's also a conceptual reason. It would be nice to understand, what does it mean? Right? Is it just, what does it mean? And so with algorithms, which are formally defined, precise, computable, maybe there's a hope of a precise definition of understanding an algorithm also. That's the hope. Okay, so here are the goals. A scale by which we can evaluate any entity's understanding. Could be human-AI combo. It should align with the standard usage of what we mean by understanding. There could be depths of understanding, and so on. And it should be precise enough that you can actually use it to evaluate. So yeah, so we want to get to this testable knowledge. Definition, and this is the full picture. So this is what I'm going to go through. So the next 10 minutes will be definitions. You might fall asleep or not, but but if you have comments, that'd be great, because some of this seems natural and the right thing, but some of it is still in development. So great, yeah. So we'll describe 5 levels of understanding an algorithm. So at level 1, this is the most basic one, you should be able to evaluate the algorithm. By sufficiently simple, we just mean that on instances that you can store in your memory or in your, whatever your physical capacities are, that's all. So it understands at level 1 if it can apply the algorithm to an input. That's it. So compute the GCD, for example. Level 2, it not only computes the answer, but also gives you a transcript. So it can provide the trace of execution, either in terms of memory content and what steps were taken, or in natural language. Okay? So show every step of show your work. That's level 2. It's simple comment here that somebody who understands at level 2 also understands at level 1. That's an obvious thing. But we'd like to maintain this for all levels, which becomes a little less clear later. So at least, yeah. Okay, level 3, it knows the algorithm itself in the sense it can produce a set of instructions that somebody else can follow and do it correctly. And do this in a language of your choice. So either in, for example, a programming language like Python, or in natural language, or convert it from one to the other. As long as you know both those languages, which we can assume GPT does, and humans may know at least one programming language and one natural language. So that's level 3. Be able to produce a precise enough description that somebody who knows this language can run it. Okay, yes? An entity. It could be a human, a Turing machine, or a GPT, a language model, somebody who claims to understand an algorithm. Yes?
But so if I ask GPT, like, write me text or something, I'd be surprised because it just write, in Python, the algorithm. But if you ask it, like...
You won't be surprised.
I won't be surprised.
Right.
But if you ask it, like, compute next algorithm for me for this, for these inputs, then I'd be more surprised.
Right. Good. Okay. I mean, this is yes.
Oh, go ahead.
No. Sure. I mean, and this has more to do with what GPT is like. And this is the case also with some undergrads these days, who might come having memorized an algorithm, and they can if you tell them, tell me the algorithm, they can write it down because they memorized it, but they may not be able to execute it on an example. Although I can assure you that GPT today can run any precise algorithm basically, even if it's ending up calling it. Yes.
So on that level, the Chinese room by Searle would understand.
Right. So up to this level, we have yes, I agree. So everything up to level 1, 2, and 3, a computer that knows the algorithm in principle can do it. Even machine translation was already done before language models. You think, right? You could convert from one programming language to another, or to assembly code, and do it correctly. Yes. I agree completely.
So can you give an example why 3 is harder than 2? Because I feel like in some sense maybe...
Yeah. So good point. Yeah. So it's precise enough, the description is precise enough that it could be executed. So I'm implicitly assuming that this entity also can execute the steps that it is outputting. You're only outputting instructions that you yourself can execute.
But I mean, if I can do level 2, then I can pretend that explaining an algorithm is what I was doing in step 2, or no?
Not clear.
Okay.
Step 2 is just you're running an algorithm on an instance and outputting everything that you did. Your variables, your steps, your decisions.
Okay, so I'm hiding how I go from a step to a step.
Yeah, and you may or may not understand.
I see.
Yeah.
I think the claims only that 3 is greater than equal to 2.
Exactly. Yes.
Equal.
Yes, so that's why I'm...
Yeah, greater than equal to. Yes.
Okay.
Yeah. Good. Thank you.
Seems to be a problem with the definition, especially with respect to humans. Like, if I came up with an algorithm 5 years ago, if someone asked me to explain to someone, I may have forgotten about it, right? Even though I had came up with it.
Right.
So there is a recall issue with humans that's not true in GPT or other models.
Oh, good. Yes. So if you don't recall it, you probably can't run it either. Right. So sure, our level of understanding can be transient in the sense that it may take us some time to reconstruct our understanding. Same thing happens when I teach an undergraduate algorithms class. After a few years, I really understand it, but I have to work it out again. Sure, I think that's reasonable. But the point is that by the time you are able to describe it precisely, you are also able to execute it on specific examples and show your work. That's all. It's not a permanent state.
So you have a sense of memory which you can access.
Sure. Yeah. Yes. Okay. So yeah, for example, write code in some way. Okay. So now comes the more interesting and more, I guess, less definite levels. And here we're actually going to split into two parts. We'll call them mathematical understanding and natural language understanding. Okay, so level 4 has, for the mathematical side, exemplification, and on the natural language side, explanation. What do I mean? So 4 for the mathematical side means that I give you some property of an execution path, and the entity can give you an example that satisfies this property of execution. I'll give you an example very soon, but let's just put the other definition alongside. Here also, you have a property, and you have to explain why this property holds for the algorithm. Okay? Now, example, yeah. It's easy to understand. It's useful to have examples, right? Like, what is the definition? Anyway, find an integer such that computing GCD 13, y makes the following sequence of recursive calls. Right? So give me an example that follows this pattern. The other algorithm that we took very seriously, you'll see that there's a human study and with GPT in a few slides, is we use the GCD algorithm, Euclid's algorithm, and Ford-Fulkerson's algorithm for computing a maximum flow. And there you could ask, give me an instance where the Ford-Fulkerson algorithm takes 7 iterations. So that's exemplification. An explanation would be something like, you're talking to somebody who knows something. Like in this case, they know the division implementation using whether you implement Euclid's algorithm using division and remainder, or you implement it using subtraction, you should get the same answer. So somebody who knows subtraction, how do you explain Euclid's algorithm to them? So you're able to take pieces that so you have this flow chart of the algorithm, and as long as you're making a consistent, coarser version, you can explain it in terms of the finer versions. That's what it's trying to get at.
So the exemplification you have there, in general, if you set up any old conditions, properties, couldn't this kind of demand tread on NP complete?
Infeasible. Even halting, you can get to, yes. Yeah, so absolutely. Absolutely.
And you don't, that's not a...
That's not, yeah, exactly. So right. So we'd have to quantify easy versus hard inputs for sure. Yeah.
And then the flip side of that, the thing that you're calling an explanation as an only language, I mean, somebody else could come by and say, look, if you understand that the division step there is repeated subtraction, you're really understanding something mathematical about it. It's not language. It's
absolutely
mathematics. So, yeah. So is this just a slightly confusing example, or did you mean for it to be so overlapping between math and language?
Right. Very, very good point. First of all, yes, the overlap is inherent, I think, and that's why we call it the same level. It's really talking about properties. And by language, mathematics itself we can view as in fact, you're an example where people like intuitive explanations. They're precise, but still the point is there's an idea conveyed beyond just a counterexample or something you can check.
I would view that as not language, but that's where you're thinking about an idea.
Right.
So the intuitive idea, I think of it as an idea, and I'll distinguish it from language.
Mm-hmm. Right. At this point, I'm calling ideas also a language.
Yeah. So then, what's left on that? What's not in the
instantiations?
What's the distinction there?
Right. So like this, for example, right? Give me an example that fits this pattern. Right.
Okay.
I'll show you a few more, but yeah. Okay. Right. So yeah, you could work it out maybe by case analysis or something without actually seeing an idea, but you do know the algorithm enough to try out many different things. Okay. So this is the full one, right? And so we have one more level that we have defined at least. And this, for the mathematical side, is extrapolation. And this means that you can answer questions about modifications to the algorithm that you understand. So in particular, if I give you a different algorithm or a variant, you can find an example where their execution paths are different, that the output is different. Or if I give you a relation, and again, I'll exemplify in a second, on pairs of inputs, I can find a pair which does different, on which the algorithm does different things. The algorithm's behavior or output is different, yes?
So at level 4, you exclude a statement of the form, this algorithm out, halts on all inputs.
Right. It's just fine.
How do you exclude that?
Say again? Sorry.
So how do you exclude, level 4, I can give you a sentence, instead of saying the GCD has this phrase. Can I not say that the algorithm halts on all inputs?
Yeah. Right now, we are the definitions are allowing for computational infeasibility. I mean, intractability.
I see.
Yeah. So if it's computationally intractable, then we don't, then we don't hold any entity to that bar. But there are going to be so eventually one will have to either put a distribution on tractable properties or something like this to actually make it yeah.
Maybe, Ravi, let me see if I got it right. I think Ravi may have been asking, would the property which says this algorithm actually halts on all inputs, or it's correct on all inputs, would that be admissible in 4A? Is that what you were asking?
Yeah.
So in other words, 4A did not seem to include those kind of statements.
Right. I mean, for now we're asking, give me a property, say halting, to go there, and an example which satisfies it. So give me an x on which the algorithm halts, if the property is halting. But yeah. Yeah, so it's not here right now. Yeah. Yes. But I do think there is a deeper issue of separating properties that are actually. Yeah. So this was this, and now I was defining. Okay, so it's extrapolation. So you can show examples where a variant of the algorithm doesn't do the right thing or does something different. And then on the natural language side, it's counterfactual reasoning, which is it can produce explanations of modifications. So if I suggest in an algorithm, how about I make this change? Then it can tell you why this change makes it a different algorithm. It's not the same algorithm. Or its behavior will be different. And I'll give you an example in a second. And similarly, it can explain a property because of which the property of the algorithm because of which the execution on two inputs will actually be different. So here for extrapolation, is the following statement true? If not, provide a counterexample. If x is greater than y, then GCD 2x comma y requires more division operations than just GCD x comma y. And then counterfactual would be something like this. Consider the Fibonacci sequence. Why do Fibonacci numbers result in the maximum number of iterations for the Euclidean algorithm? Yes?
Yeah, why do you think that natural language explanations are the right medium to assess this kind of understanding? Because it seems like we can produce them easily by having memorized stuff.
Explanations? Because this includes properties of the algorithm which are not explicit in the definition of the algorithm or in code that runs it. So for example here, we have here, why do consecutive Fibonacci numbers result in the maximum number of, so it turns out that if you want to maximize the number of times a GCD algorithm runs, number of iterations, number of operations, then the worst thing you can do is pick consecutive Fibonacci for that size.
I guess just thinking about understanding, it seems like there are many places where I can produce the right words corresponding to the right explanation, but actually not understand what I'm saying at all.
Yeah, like if, you know, if GPT has read about the algorithm on Wikipedia and this happens to be there, then, you know, it could just like copy and paste essentially the Wikipedia explanation or something. But also I'm wondering, why do you call this counterfactual reasoning and extrapolation?
It's a little bit more than the algorithm itself, right? It's a property that is implied by the algorithm.
Yeah, like for 5A, it seems like meta reasoning about the algorithm.
I mean, yeah. Indeed, maybe. Yes.
So it seems at level 5, maybe even in level 4, you have kind of made the connection from the original algorithm to this a new computational problem, almost incidental. It's very hard to kind of, it seems like a computational problem that is kind of related to some properties of the original algorithm, but the connection seems very hard to kind of measure how this problem can be. Like I can create, say, a complex number theory problem which is incidentally connected to the complexity of the, say, some GCD algorithm. But the problem that is attached to it is just so complex.
Oh, I see.
So it's kind of a hard to imagine understanding of that to have any understanding of it.
Right, right. So the claim is not understanding the other algorithm also, but understanding this algorithm well enough that you can separate it from other algorithms, in particular variants, but I have not defined a distance between, you know, how much you're allowed to modify and so on. So for now, it's just saying, can you tell if this algorithm is different from another algorithm, A prime?
My worry is that you may fail to produce an answer to 5, even if you know very well what you're understanding in some sense.
Yeah, that's a valid point, yes.
See, I'm obviously misunderstanding something because, okay, so with those labels, I had thought that you were trying to distinguish between two possible entities, one of whom had a mathematical understanding of this algorithm, the other who knew the fact about this algorithm, like the code, etc., but and understood language extremely well, but did not have a mathematical understanding. But when I look at these examples, I feel almost opposite, that on the language side, you know, the task given on the language side, if somebody solved those, it would convince me more that they have a mathematical understanding than on the mathematics side. So obviously you mean something very different.
The names are certainly...
yeah, so, but neither of them seems to be the kind of thing that, you know, if I were to assume that there's an entity that just understood level 1 to 3 about this particular algorithm, and then we make this entity forget everything else except level 1 to 3 for this algorithm, and incredible facility with language, and then they say to this entity, explain to me, answer these questions, you know, that entity I don't find represented here.
But that entity who only does 1, 2, 3
and has language ability.
And has language ability independent of...
And reasoning with language, but not with math. You know,
yeah.
So that's what I'm missing, right? So I was sort of expecting some flavor of that, but maybe that was a mistake on my part. So I'm trying to understand what this distinction is getting at.
Right. So So maybe I'll try one more example. So let's say you're trying to compute maximum flow. The example in level 4, the exemplification question would say something like, give me a graph where certain property holds for the execution, such as it takes the direction of an edge changes 3 times. That would be the exemplification. Now that takes, you need to understand the algorithm at some level to be able to produce this. But I'm calling that kind of, I don't know, maybe computational understanding, or at the moment it's called mathematical understanding. Now, as opposed to somebody who knows how to find a path in a graph. Let's say they already know the algorithm for finding a path. Then you can say, describe the fold crystal algorithm to someone who already knows how to find paths or shortest paths or so you're able to translate this algorithm into blocks that they already know. And that, I'm thinking of that as language, broadly speaking, reasoning. Right. Yeah. Yes.
Your 5B example, isn't that just a theorem?
Yes.
And you could make it arbitrarily complicated.
Right.
And depending on, if you can do that, you show how deeply you understand that algorithm or how much, how familiar you are with it, that you can prove that or show that.
Right. No, yes, that's right. Yes. So by the time you're at 5A and 5B, I would typically, can't prove it. You should know why the algorithm is correct also. Yeah. But that's something I would like to say. Could we possibly state a theorem like that? That's a candidate theorem. So one candidate theorem is that these levels are actually non-decreasing depth. If you understand a greater level, you want. Another theorem would be, by the time you're at this level, you can produce a proof of correctness of the algorithm. But I can't prove it. Clear question?
Yeah, so in the counterfactual example, you're imagining that there's a change to the algorithm, right?
Yeah.
I suppose, if the change is sufficiently large, such that it becomes really it's a much more complicated algorithm, right? Then you're presupposing you have to understand the original as well as the changed algorithm.
Yeah, maybe there is, maybe that's I mean, it's not explicit, but certainly we're not assuming that in the definition. But I'm not sure if that follows for a. It's not the intent, but we have to be careful that if that follows, and then that would not be such a good definition at all. Yeah, we have to somehow restrict. Yeah, but thinking more like, if you made this change in this step, right? Would that be fatal, or would it result in a different behavior? And it's not clear how to model changes like that without saying another algorithm.
So sorry, maybe it was already said, but is like knowing a proof of the correctness of the algorithm one of the levels here?
Not yet, not in this definition. I'm conjecturing, not conjecturing, but I'm wondering if level 5 implies that an entity who's able to have a level 5 understanding actually knows a proof.
But it's not. You don't know.
I don't know.
Okay. Yeah. So it might be lower or somewhere in between.
Yes.
Okay.
Yes. Exactly. Yeah. So these are there is room for a theory. Okay. Yeah. Okay. So we did this survey with these two algorithms. We developed the questions, and there's a simple algorithm and a little bit more advanced, but typically taught in undergraduate classes. We had doctoral students, undergraduates, and versions of GPT. And the hypothesis is that the understanding depth captures this hierarchy does capture the depth of understanding, and newer generations will do better. And maybe there will be a performance gap between natural language reasoning and mathematical reasoning for language models. Okay, so just a couple of slides. So certainly for the depth, it's consistent. So here I've separated into undergraduates, doctoral students, and GPT. So all of these are undergraduates who have done the algorithms course, doctoral students who've done a graduate algorithms course, and then just GPT. And here I've not told you what the questions are, but the survey is available publicly. You can look at it if you like. But basically,
sorry, the questions don't correspond to levels.
They do, exactly. The questions correspond to levels, but we don't use the same question we generate lots of questions and mention in a second. Yeah, exactly. They correspond to levels, and so the score as you go along drops with the level. That's what you'd expect because it's kind of harder to do well at the later levels. Blue is undergraduates. This brown is doctoral students, and the green is GPT-4. Yeah. So that's for first. Second, it's just that each question was scored 0, 1, or 2. Okay. That's all. So in the case,
like you or your team, or
yeah, by Measurable and yes, by hand. Yeah, even the GPT answers were scored by hand, like you would for an undergraduate exam. Yeah, exactly. So there's no automated scoring. Yes. That's correct. Yes. So we produced many, for the case of GPT, whereas the students took only one survey, 5 questions, that's it. With GPT, we produced many different versions of the survey, randomized, and ran them all, and then graded by hand.
So different numbers?
Different numbers, but also some variations in the questions, variation in the input graph. Yes, I guess you could call it different instances, yeah. And then here's maybe a slightly, yes, sorry.
One quick question just about the last.
Yeah.
Isn't Q1 to Q2 kind of surprising? Because my interpretation is Q2 is with chain of thought, and Q1 is just give the answer. So then this seems to suggest chain of thought does worse, which I think is surprising. Right?
Yeah, I mean, this is only till 4, GPT-4. Well, let's see. We're not asking it. We're saying produce a transcript of your work. That's correct, yes. So I guess you could call it chain of thought even in the earlier models, right?
But even in humans, it's true.
Easy
chain of thought.
We haven't run it on O3 yet. I would guess that, if I had to guess, it should be similar, yeah.
Q1 is just like asking for the answer directly without any trace. But even a human would probably do like the traces, like in the
Yeah, on the side somewhere. Yes. But then when they copy over, they make mistakes and all these things happen. Yeah.
Okay.
I guess how is Q2 evaluated? Maybe that's like how do you evaluate a correct score?
Oh, yeah. I'll put it up there. But basically, you lose a point if you make an explicit error.
Yeah. Okay, that makes sense. Yeah. All right. Yeah, that's one.
This one is looking at. We want a little bit finer. Are you worse on later questions? Suppose you got everything right up to question 3. What's your chance of getting question 4 right? Right. So you want to kind of do that. So here we're looking at the difference in the question, and it's negative. So you're doing worse question by question. You kind of saw that in the previous trend, except GPT did better on the coding level 3 than on level 2. So there it got better.
Maybe that's chain of thought more than Q2.
Yeah. But everything else, humans and GPT, basically did worse on later questions. And this one is what I was saying. Suppose you condition on being correct on all previous levels, then your chance of being correct on the next one is higher. So blue is just without conditioning, so it just goes down. And brown is if you got everything right till now, then what's the chance of being right on the next one? So if you have good understanding level 3, then it's more likely your understanding level 4 higher. Is that, I guess, what you'd expect? I won't walk you through the other 2, but I'll summarize in the discussion what we thought about it. But now, of course, there are more classical things about education itself, not just algorithms. And I don't know how to make these things precise, but there is a lot. Yes.
Sorry, just on that last slide, there's kind of like a U shape. Am I reading that right for the conditioning thing, right? So it's like if you made it through the middle levels, then that's a good prediction of you'll be.
Yeah. So by the time you made it to level 4, you're nailing level 5.
Right. But
if you got
doing well on question 1 is not a good predictor.
Yeah, exactly. Exactly. Yeah. Even 3, you're kind of getting 4 right, but But if you got level 4 right, you're boom, level 5. Yeah, exactly. Yeah. So it's just consistent with what you might say. Okay. So here's just wrap up and questions. So on the code generation, GPT was basically perfect. For what we call natural language tasks, the language models were consistently better than on the mathematical reasoning tasks. And of course, there's an overall improvement in the versions of GPT. And as far as this test is, this 2 algorithms and this survey is concerned, GPT-4 was better than undergraduates who had done the course. Not quite as good as graduate students, but now, can we conclude anything? No, but starting point. There might be higher levels. For one level that we like to see in an algorithms course is transfer learning. You learn about a few algorithms, and then you want to be able to use your understanding when you learn a new algorithm. and this is not captured. Oh. So this is, if you want to take the survey, that's the QR code. Yeah. Sorry.
Yeah, thank you for the talk. I was wondering if you could go back to the hypothesis one.
Yeah. Yeah.
Yeah, so I guess the question I have looking at this is it seems like the hierarchy you propose is a good model for example, the undergraduate understanding of material, right? If the undergraduates do worse and worse as the tasks get harder, so it seems like a good model of their knowledge. And the doctoral students who probably all know what's going on, they all do pretty well.
Yeah, except on the coding where they may. Yeah.
Sure. Yeah. But that doesn't seem to hold for GPT-4, right? The GPT-4 graph, it's not doing worse as the task gets harder. And so I guess it seems to me like one interpretation of this graph is that the taxonomy of understanding that's proposed here is a good model for human understanding, but maybe it's not doing the same thing for language models. So that the harder tasks in this hierarchy are not necessarily harder for language models the way they are for and so I wonder, based off of that, then, if you think there are maybe different sorts of tests that would have to be done for language models in order to actually capture that.
Yeah, it's a good question. This is what I tried to highlight in the discussion, that GPT does really well on the coding questions, even if you ask changes and things like this. And I guess, do we understand why it's so good at coding, besides the fact that there's so much code on the internet? I don't know. But as far as your question is concerned, I don't know. I don't think this hierarchy is anywhere near the right answer. But maybe this level, being able to communicate an algorithm, which is what level 3 is trying to capture, needs to be refined.
Yeah. Actually, given what you see here, given this last question, when you showed the U shape, shouldn't it, if you just condition on the first two, or even on the second one, that should give you high chance of success on all the rest, because the rest were not there wasn't much meaningful conditioning to be done on question number 3, right? So since it's doing so well already, no matter what, then the conditioning is most extreme on question 2. So if you changed your U shape and just instead of doing conditioned on all the previous ones, just to condition on number 2.
Interesting. Yeah, good point. Compare conditioning on everything with just conditioning on question 2.
Yeah, good. Yes. I'm missing one kind of understanding that I have an intuitive feeling about. So I'm a journalist. I write about a lot of stuff that I can't do the nitty-gritty legwork. I couldn't write algorithms about LLMs. I write about this stuff, and I think I understand something about this stuff. And aren't most humans, like a well-educated human, understands a lot of things in the world that they don't know the details about?
Right. Good. So this
I might make give you some things on level 4 about explaining what certain things do without having the depth of the knowledge.
You're right. I mean, in fact, yes. So the intent was that somebody who can't execute the algorithm really doesn't understand. Nevertheless, level 4B is getting at being able to explain something correctly, even if you don't understand the mechanics. And this we see in language models. We ask often, if you want to learn a mathematical concept especially, it's great to interact with GPT. And it may not be able to actually compute this function or whatever it is. So yeah, this is an anomaly with the
In fact, wouldn't we have people who do, who can work with theoretical algorithms, but may not be able to go and then, churn out executable code?
Good. So they don't need to know Python, though, but they should be able to write down a precise description of the algorithm. So theoretical people who know the algorithm will be able to write down in whatever language they, English.
Right. But would you put it past somebody to be brilliant at figuring out exactly what's going on, but not be able to pin down every detail of the pseudocode?
Yeah. So yeah. So their version of the algorithm has some approximation, some fuzziness in it, and they still have one would say they still do understand it, even if they can't quite execute it all the way down. So that's close to what you're asking.
Yeah,
and
what do we expect from a good politician? I mean, they have to make decisions about the world, but they don't understand the detail.
Right. So
they have to have good people that tell them.
So it's almost like you want a correct, approximate course version should. Maybe level 4B should move somewhere else in the picture. Yes.
Santosh, what do you expect for the survey if like the sample size increase? So it's kind of small, it's like 10, 13.
Yeah, it's a good question. Measurable is planning to run a longer survey with more algorithms also, and some of the questions created by undergraduates and so on. So we'll have to see. The GPT survey had large numbers. We ran 60 iterations, all of them. Yeah. So, but of course that's yeah.
Sorry.
Yes.
So there's that work you probably know by Shafi about self-proving models.
Yeah.
So where they train LLM to also produce a proof for the GCD exactly, right?
No, I don't know this. Yeah.
Okay. So what they do is they take the GCD problem and they try to, so they train it with a verifier that verifies that the answer is correct, because you can have like a simple proof with like some Bezout coefficients which are just numbers. And they do it, and they have a method to train it, right? And they say that it's better than, or at least it generalizes better when you train it this way for producing a proof than if you just took a regular model and asked it to also produce a proof. So like the training changes, right? And now, I mean, it might be interesting to look how does that model perform for your levels, right? Because it was forced to also know the proof. But like during training, you forced it. But proof about correctness, I mean, I don't know which level it is, but probably like 4 or 5.
Yes.
So I just was wondering
if it's an interesting point. No, I haven't seen this. That training with proof produces a better outcome.
So I don't think it produces a better outcome, but it produces. It more often produces a valid proof than if you just took a regular model and asked it to also produce a proof. I don't remember exactly, okay? But thank you.
So it's kind of relates to the talk before the lunch of variable binding. It seems like a more of an algorithmic version of variable binding generalization. So in that talk, they had to like train the model from scratch, so it doesn't have those kind of, doesn't scoop the thing from the data itself. So the problem with comparing with this large language model, a lot of those things could be scooped from the data, even 4 or 5 level questions.
Yeah.
So it seems like if you really want to kind of compare it, you have to kind of build something where you are like more careful about what is the source of the data.
Oh, sure, yeah. So we tried to design every question that was in the surveys. Of course, we did a Google search and also looked in the books to make sure that these questions or minor variants of these are not already there. That doesn't mean it has, somehow we encountered something similar. But yes, we're trying to make the surveys somehow be out of the data distribution. Yeah, which is not a. So, right, so this is I was going to go to another boundary issue with language models, which is about hallucination. But given that there's 10 minutes, maybe it's...
We started 5 minutes.
Okay, at least I'll state the main thing, yeah. Yes. So once again, so first of all, hallucination, yeah. So, yeah, can you tell which one is the hallucination? Yeah. But, actually, neither of them. These are actual images. But again, taking Umesh's advice, this is the theorem. But I have to explain what that means. Calibrated language models must hallucinate. And the theorem is a lower bound on the rate of hallucination. So I'll basically take 10 minutes to define calibration and hallucination and the model. Okay, so this entered the dictionary in 2023. So as one of the definitions of hallucination, a plausible but false or misleading response generated by an artificial intelligence algorithm. So I think we encountered this, so I won't put up all the news examples. Okay, so just this is where you bear with me for a minute. So in pre-training, we're thinking of a language model now. Now here I'll be a bit more specific with language models, but still very general. The architecture won't matter. So you don't need to know, I don't need to know what a transformer is or so on. But at the end of the day, it's a distribution over documents. And the way it's pre-trained is by maximizing the log loss, the expected log loss. This is what we're assuming, that you produce a language model by pre-training it to maximize the expected loss over some training distribution. And of course, once you have this, you can now complete prompts or generate documents by doing next word, next word, next word. Yeah. Right. So yeah, just to put that point down, if this was your entire data set, these are the probabilities. And so, you know, first token, 40% chance it's given that it's the next token, it's 50% chance it's sun, and then 50% chance it rises. So you produce the whole thing with probability 10%, product of the conditional probabilities. And so it makes sense that the log of the probability with which you generate the document is just the sum of the logs of the conditional probabilities, which is exactly what you're maximizing when you pre-train. Okay, so now what is hallucination? So we're going to actually have two explanations of this, the theoretical explanations. One of them is going to refer specifically to arbitrary facts. So what do I mean by that? So systematic facts are governed by rules, right? So they may follow from others, like implications, or they're just not too many. The capital of Oregon is Salem. There's not that many. It's far fewer than the parameters of the model. There's no statistical need to hallucinate here. Right? There are algorithms for these things that, in principle, could be learned from examples. On the other hand, with arbitrary facts, there are few or no rules. So, and they don't follow from others. So, for example, who ate what, when, where, and why? On February 7th, Ravi Kannan ate Baba Ganoush at Alibaba. Is it true? Maybe. I mean, yeah. This is a restaurant, that's a dish, it's a person, date, maybe. Okay. Suppose you know this. Can you say anything about what Umesh ate yesterday? Okay. Anyway, Adam Kalai's birthday is April 1. It's true. At least as far as you're concerned, it's true, right? Okay. Anyway, so those are arbitrary facts, right? If I know the birthdays of everybody in this room except the last row there, no information. Okay? Okay. So far I'm saying something very obvious. But now, so here's the point. I'm getting to the theorem that says pre-trained language models must hallucinate. Okay. So of course you don't have to hallucinate. You can always output a factual thing. The sun rises in the east. Or you could memorize facts in the training data, which are facts, right? Not all, but fact, and then output only over a distribution over facts. So there's no hallucination here. But the trouble is that these are not calibrated. Such a model would not be calibrated to your training data. Now I'll tell you what calibrated means, and I'll tell you in a second. But that's the point. And pre-training induces calibration. Okay. So here's the main intuition. Pre-training today optimizes the language model by maximizing log loss to match the data distribution. And really, as an implication, it is calibrated with the data distribution. Future documents from this data distribution will have some rate of unseen factoids. Factoids meaning there could be facts or hallucinations. We don't know what they are, but they are candidates, plausible things. And so you have to produce, you can't produce only the training data because you're calibrated. You have to produce things that you haven't seen also. Otherwise, you wouldn't be calibrated. And therefore, when you're producing an unseen factoid, if the rule that says fact or hallucination is arbitrary, we'll define that in a second, then you will also produce hallucinations. So that's the intuition. So I'll tell you what is calibration to make this precise. So the classical, the 1980s definition by economists is this: for days on which you predict the rain is 20%, look at all the days when you predict 20% rain in the year. Among those days, it actually rains 20% of the time. That's all. So it's very easy to be calibrated, because you can always say, I simply predict the average probability of rain every day. So suppose the probability of rain in Berkeley is 10% over the course of the year. Every day I'm just going to say 10%. So it's not very accurate, but it is calibrated. Because on days when I say 10%, which is every day, it is 10%. It's a very weak notion of accuracy. Okay. Now, so we have a data distribution P, and then the language model learns some distribution P hat. And what it means to be calibrated is that whenever it says the probability is T, the language model says the probability of some document is T, over all such documents, the actual average probability is T. Right? So in the bucket on which you're saying the probability of these documents is 0.1, it really is 0.1 on average. That's right. Okay. And you can have approximate notions. So just to make this, it might be a useful thing if you haven't seen it before. There's a true distribution over documents, right? These are the probabilities. And think about a coarsen distribution. So you just, somehow you coarsen it. All that means is that you put down a partition of this. Within each part, you make the probability just the average, just the average. You could have picked the entire thing as one part, but let's say you pick subsets. You choose the partition, and then within that you replace by the average. So that's this. And this is the coarsen distribution. Now, why am I telling you about coarsening? Because the miscalibration, so first of all, you are calibrated with another distribution if you are exactly some coarsening of that distribution. That's it. What I defined before is equivalent to this. Distribution P hat is calibrated with distribution P if and only if it's a coarsening of P. That's the lemma. Now, of course, you may not be perfectly calibrated, so you need to talk about miscalibration. How far are you from being calibrated? And for this, we just say, look at some coarsening of the true distribution. How far are you from the closest coarsening? That's your miscalibration. That's it. That's the miscalibration. The distance between you and you choose your coarsening. Okay. And the point is that calibration reduces the pre-training, this loss, and as a result, it's encouraged by minimizing the log loss or maximizing the log, and so we have also extension approach. Okay, now, yes. Calibration decreases. Yeah. So if you have a distribution that's not calibrated, there's a simple operation you can do, a reweighting, which will reduce your log loss. Yeah. So take a, yeah, exactly.
So you just average out.
Exactly. Yeah. You have to be a little bit careful because it's not true in each bucket, but overall it's going to be true. And the proof actually uses Jensen's lemma to make sure that it's, but you get a strict decrease. So exactly, yeah. So indeed, the technical report for GPT-4 from 2023 shows that it's really well calibrated on their whatever test set they checked on. This is the probability of the answer and the probability of no, when it says the probability is 0.6, it really is correct 0.6 of the time. So this is there. They didn't try to calibrate, they just pre-trained. Right, so, okay. Now, so yeah, quick. There are many reasons why one could hallucinate, but I'm going to focus on because of unlearnable or hard to learn fact distributions. And so this example may be more useful than the theorem. Suppose this is your training data. You notice some pattern here. What's the model that you would come up with? These are the 10 documents you're trained on. Sorry. Yeah, I'm so sorry, terribly sorry. the text in the blue says Alan Turing was born on 6/23/1912, which is actually a fact. And everything is a fact here. You know, so excuse me, I'm so sorry. Alan Turing was born on 6/23/1912. June 23rd, 1912. Okay, that's half the time. So with probability half, all the blue is the same statement. Sorry, and the other half is other birthdays, which are also true. So this is the model, right? Half the time you say Alan Turing was born, and half the time it's a random name on a random date. That's the model from which the data came. And if you pre-trained, you'd want to pick up this model. This is the model. This would generalize the distribution. Now, but it's going to produce hallucinations 50% of the time. Why? Because every time it picks random name and random date, it's likely to be wrong. Doesn't matter how much you trained on. And on the other hand, if you did what sometimes people who first do log laws do, if you maximize the probability, the expected log loss over the data rather than the distribution, then you will end up just regurgitating the exact distribution you were trained on, which is completely factual, but it's totally not calibrated, right? Because you're over-representing these facts. So I'm going to go faster and say basically in this model where facts are arbitrary, you get a lower bound on, there is one nice thing here, which is this, that the probability of your language model hallucinating is lower bounded by the fraction of unseen facts. If you've seen all the facts in the universe in your training distribution, then you don't need to hallucinate. Statistically, you don't need to hallucinate. But if there is some fraction of facts that you haven't seen, and you've only been trained on good data, only on facts, nobody has given you bad data and so on, you will still hallucinate at that rate minus the miscalibration of your model with the training distribution, minus a term that depends on the fraction of facts in the data. That's the theorem. Yes.
I didn't follow in the previous slide.
Okay.
So why when you're calibrated do you spill out onto unseen facts? So you're only calibrated with respect to that.
Not the training data. You're calibrated with respect to the training distribution,
which was
from which the training data was drawn. So when you are maximizing the log loss, you're not maximizing on the data. You're maximizing the expected log loss over the training distribution. And that leads to calibration with respect to the training distribution, not the data. Yes?
Sorry, why is this given in facts and not in terms of facts and not in terms of strings? So.
Oh, every string, this is a highly simplified model, idealized model, and the point is that even in this ideal model you'll hallucinate, and the model says that the language model is generating documents, and the documents are what we're calling factoids, so they're either fact or hallucination. And so we're asking, what is the probability that it generates a document which is a hallucination?
Yeah, I guess calling them facts just seems kind of misleading, because what makes it arbitrary versus systematic is whether the string has some interesting relation to the other parts of the document, and not whether the fact follows from other facts.
Oh, good point. Yeah, so sorry, this totally idealized model here. So every document has just a single factoid, nothing else. Right? We're making these conditions as amenable as possible to not hallucinating, right? And then saying, even here you will hallucinate. So you get to do this since it's a lower bound. Yeah. Okay, so this is the theorem. And let me just now say one nice thing here, which is how do you know the fraction of unseen facts? Right? You know what you've seen. How do you know what you haven't seen? Or what fraction of what's there you've seen? For this, we have the good Turing estimator, which maybe some of you know. It's a beautiful theorem that says that you draw samples from some distribution, and I just want to know what fraction of the support have I not seen. And the estimator is just in the data that you've seen, look at the fraction of data that has appeared exactly once. So the unifact or monofact fraction is very close to the fraction that you haven't seen. It's a nice exercise if you want to try that out. So, in fact, we can replace the statement about, and then it's highly concentrated there and so on. So we can replace the statement. So this is the theorem slide, that this was unique. Look at the fraction of unique facts in your sample size n, minus the miscalibration. So if you're highly miscalibrated, you don't need to hallucinate, minus this ratio of facts to hallucinations in the data out there. You only see facts. And this is a sampling error, roughly 1 over root n. And so basically, this is the. I want to just say one thing about other kinds of hallucinations. So you could have calculation error. We saw this morning that even more recent versions say 9.9 is bigger than 9.11 and so on. And there are model misfits too, right? I mean, your model, we didn't say anything about transformers. Maybe the model itself is incapable of learning something, even though the thing is learnable, and so on. So there's a different explanation here by showing that the probability of hallucination can be lower bounded by the error of a classifier, where a classifier is trying to use the language model to decide is this fact or fiction. So I won't I won't try to explain it, but let me just say that if you have a high misclassification rate, then you will have a high hallucination rate. And this error could be for whatever reason. It could be because it's statistically the class has high VC dimension, or it could be because the model doesn't have enough computational power, whatever it is. Whatever the reason for the classification error, the hallucination rate will be twice that, minus error term that depends on the fraction of facts. Okay. So I'll stop with this summary slide and some questions. Things like country capitals, they're not rare. You see them all the time, so there should be no reason to hallucinate. Here also there are few rare facts. There should be low hallucination. Things like birthdays, and there should be high hallucination. People try to add new facts to training, but this can actually hurt, because if you add them once and so on, it doesn't. Duplicating data doesn't help either, because it may reduce hallucination, but we'll just be regurgitating more. And so this is a question that I guess people are thinking about a lot, which is how do you reduce hallucinations? In particular, my co-author is working on it last fraction of his time. You want to get models to say, I don't know, rather than hallucinate. And on the other hand, this type of post-training will reduce, will increase miscalibration, or reduce calibration, which may not be a bad thing. And indeed, it happens. So for GPT-4, where they use this reinforcement learning with human feedback to reduce the hallucination rates, after that, which the model generally is agreed is better, your calibration is no longer the case. So there's this fundamental trade-off between these two things. This is from the same technical report. Okay, so there are many open questions. You want to transform this pre-trained language model into something else before you actually use it. Like we do, right? When our ears, we don't just are not true to the data that we hear all the time. We actually modify it before we output or interact. But how to do this, how to measure the cost, what's the right metric, not clear. There are things more fundamental about language models, I think. Like why does this type of statistical learning allow you to learn longer range structure or more complex structure? Any explanation would be great. Just look at it. Yeah, I like this one a lot. It's not precise yet. It seems that by training GPT on the web, or a language model on the web, it gets to do other things. It's using its internal representation to do, in quotes, reasoning on tasks it may not have been trained for, learn structure and so on. And maybe that's what language more broadly means, rather than natural language or form to communicate. And what does this mean? Yeah, so are there simple guidelines that would make pre-training or induce what's coming out to be safe without trying to deal with each problem that comes up. So I think that most humans, for the most part, are ethical, and somehow that came about. And I don't know what the conditions were that set it up, but could we set up these conditions without having to police the output? Finally, and going back to the beginning, can we have an algorithmic test for an entity's depth of understanding of an algorithm?
Any more questions? Safety at the bottom. How does this relate
to understanding? Algorithm, yeah. So I mean, I think it's a more generic question, about. I guess the idea is that if you, take an example. Self-driving cars are likely to do something bad because they don't really understand what goes wrong when these extra situations. A driver who learns driving in a city or in a parking lot will generally do well no matter where you put them. We don't have those confidence for a self-driving car or an AI somehow because we don't understand. We are not confident that it understands. So maybe if it actually understands what's involved, then it's going to be safe. It's a exercise.
Yeah, this is sort of just a wild guess. Could that be in terms of the algorithm for the GPT? Maybe OpenAI just sort of fine-tune the domain knowledge related to algorithm and coding, like the virtual lab yesterday, the talk. They fine-tune they have access to OpenAI's code, and they fine-tune the code that relate to the biology part domain expert. So expert system. Then they basically have produced better result. Maybe would that be? Can you do sort of a control kind of experiment? Say like, I don't know whether DeepSeek also have done that kind of thing, but this is maybe.
No, it's an interesting point. Maybe it's possible that more effort went into coding training or whatever. But still, the question merits. You can ask. Sure, they put in more effort on training, more weight on the data about programs or correct programs. Is it still able to reason about the algorithms that it knows how to code? It would be nice to evaluate that.
One thing about understanding, one way to think about, at least I could think about whether someone understands something or not, is how brittle their understanding is. Right, so somebody can just know something from one vantage point. So we have one representation of it. We can ask them all the questions you want in that representation, and they can answer it. But if you change your viewpoint somewhat, or you reformulate it in any way, right? So usually there are multiple ways you can look at something, and over time your understanding increases because it becomes less and less brittle to these changes in viewpoint. So is that something that you can capture? Is that something you've thought about capturing?
That's a great suggestion. I mean, that would be, I don't think it's captured, at least not explicitly right now. Maybe the right way to ask level 5 is not if the algorithm is changed to some other algorithm, but if the algorithm is changed to be presented in a different way, are you able to?